All right, everybody, we're going to go over Series and Sequences Gateway 5, which is in course content, and I struggled to fit this on the screen, so you should bring up the PDF and look at it while you're looking at this. So first we're going to go over the true-false. First one says, if AN diverges, does that mean that this guy diverges? And the answer is no, because if you just start with 1 over n, it'll diverge, but if you work on it with the alternation, it'll converge conditionally. So that is false. So the alternating series does converge, harmonic series does converge, even though the original does not. All right, the next one says, again, same hypothesis. If this diverges, so does its absolute value. And that is true. Think of it this way. If the absolute value one did converge, then the test for absolute convergence says that the original hypothesis, the original one, would converge, which is false. So just think about it the other way around. So that is true. That's just a different way to say the test for absolute convergence. All right, third one here. It says that if AN diverges, so AN's no good, and it has the 0 this time. 0 is less than AN is less than or equal to BN. Does that imply BN diverges? True again. That's just the comparison test in the direction where the bigger thing. If you're bigger than divergent, you're divergent, right? And if you're less than convergent, you're convergent, assuming positive terms in both cases. All right, last one says ratio test is no good for p-series. Doesn't tell you anything. Bad for 1 over n to the p. That is true, because when you take those limits, for example, let's do 1 over n squared, you would do the plus 1 and then times the reciprocal. These limits are always going to go to 1 as n goes to infinity. So those are, and that's indeterminate for the ratio test. So yeah, the ratio test is not useful for p-series. So that is also true. All right, the next few are about computing limits. The first one is actually limit of a sequence on all of these, so be careful. When the thing you see with just parentheses looks like this, so I got some expression, and then I got this thing, and it's got parentheses. That's a sequence, okay? And for a sequence, remember, it's really just looking, if you're going to graph it, you're just looking at like the horizontal asymptote. So you're looking at the ratio of the leading coefficients, which are the n squared terms, even though they're not in order. So it'd be 7 over minus 1, so that limits to minus 7. Now that sum would diverge, but that's not what I'm asking. I'm asking what's the sequence go to. Because the sequence, right, would have to go to 0 if we were going to sum it. All right, the next one is a sum, and here I'm asking you to compute them if you can. So they're either going to be geometric or diverge, basically. So here, going 0 to infinity, and it's written this way. And so what you need to do here is you need to split it up. If you split it up into this thing minus this thing, those both converge, and we know what they converge to. 1 over 1 minus 3/9 and 1 over 1 minus 7/9. So that's the geometric series formula. So you don't add those, you subtract those, and that would be your sum. Because you can separate them into two convergent things. Now the last one is also geometric, but it's pi over 2 to the n. Pi over 2 to the n, so here pi is bigger than 2, so pi over 2 is bigger than 1, and that means you have a divergent geometric series. So no good there. All right, the next page is about convergence or divergence, and it says clearly use what test you're doing. So the first one, this one's kind of tough. This is 1 ln 2 to the n, and first you have to use a logarithm rule. If you bring down that n, you have this, and ln of 2 is a constant, so this is just a multiple of 1 over n squared. So this is a convergence p-series once you rewrite it, because p is 2, which is bigger than 1. All right, the next one, man, it's a tough one. It's n factorial over 2n factorial. So I'm going to use the ratio test for this. And I think it converges. So let's see, n plus 1 factorial. On the bottom, remember, it's 2 times n plus 1, so it's really 2n plus 2 factorial. And then times the reciprocal. And you're going to expand those factorials to cancel some stuff. So this is going to be n plus 1 on top. You're going to cancel the rest of the factorial with the rest. And then down here you got two terms before you can cancel the factorial. 2n plus 2, 2n plus 1. You take the limit of what's left. You've got a coefficient of, well, you've got an n on top, and then you've got an n squared on bottom. So that's going to go to 0, which is less than 1 for the ratio test. So that is convergent. Let's see. Next, this one, it's tempting to do the ratio test right off the bat, but I'm going to say don't do that because of the plus sign. So you're summing this. I suspect it is convergent. So let's separate it into two things. This is a convergent geometric series. So really all you need to know is whether this thing converges here. And you can do that so if you're just thinking about this thing over here, you can do that with the ratio test, or you can say, hey, this expression is actually less than 2 to the n over 3 to the n, and that's a convergent geometric series. That's the fast way to do it. But you can do the ratio test on the part I circled also. But either way, you get the sum of two convergent series, which is convergent. I would not do the ratio test right off the bat with that plus, because you're just going to get a disgusting algebraic thing to evaluate. All right, next is conditional and absolute convergence. So the problem is this. And so when you see an alternation, you should start thinking about the alternating series test and does it work without it. So if you forget about the alternation for a minute, this thing you know is a divergent p-series. I don't know why n is starting at 2, but it's fine. But however, with the alternation, the alternating series test says you just need the rest of it, so this part, to decrease to 0. And if you graph it, it totally does. So this is convergent by AST, so this is convergent, but the absolute value is not. That makes it conditionally convergent. All right. So we got two theorems at the bottom to state the integral test. So the integral test has a couple things. Basically, how do I want to write this? I want to say that if the an's are the inputs of a function, then this converges if and only if the integral converges. So you can put the same starting point at the bottom, but it doesn't really matter where. We'll put a k here. So, and I think these also need to be positive terms. So there's some fine details, but the main point that I want to make is that basically you just integrate the series, and it works in both directions. That's the unique part of the integral test. If the integral converges, so does the sum. If the sum converges, so does the integral. So sometimes we'll even figure out sums by doing the integral. So there are some fancy tricks you can do in later classes with that. So the key point is that it goes both ways. All right, the second one is actually the definition of convergence of a series in terms of partial sums. So we're going to call Sn the sum from 1 to n of a series, so the partial sums. And we're going to say that this converges if and only if, because this is really the definition, Sn converges as a sequence. Because that Sn is the sequence of partial sums where you take the first one, and then you take the first two, and then you take the first three. That's the sequence of partial sums, and this actual sum converges if and only if that sequence converges. It's both directions. That's exactly what it means for a series to converge. It means you add a bit, add a bit, add a bit, add a bit. I think that sequence, does that converge? All right, that's it.